Hi everyone, and welcome to today's ATAR Notes Chemistry Unit 3 and 4 lecture. So before we get started, I just want to let you know a little bit about ATAR Notes and what we do. So ATAR Notes provides heaps of free resources to help you get the best out of your study. So we've got hundreds of downloadable study notes, these online lectures which are spaced throughout the holidays throughout the year, an online Q&A to provide discussions about your particular subjects and to get extra help, videos to provide online engaging revision, newsletters, and an ATAR calculator to see if you're on track to get your goal ATAR, articles with heaps of study strategies and tips, and heaps more on our website. So make sure you check that out. It's a very useful resource. And we've also got heaps more resources through TuteSmart, which is our online tutoring from recent Year 12 graduates. We've also got our study guides, which are some printed revision materials, which step you through how you can get your best possible marks and provide you with heaps of great study notes. And then we've got Ed Unlimited, which provides all of the top study guides all in one online platform. So these are all really great resources, and I recommend that you check these all out. We also want to give a special thanks to our sponsors, so that being La Trobe University, RMIT University, Deakin University, UTS, and Macquarie University. So a little bit about me. My name's Amelia, and I graduated from Matthew Flinders Anglican College in 2021. When I was in grade 11 and 12, I studied biology, chemistry, methods, literature, food and nutrition, and Japanese. I'm currently a second year student at UNSW, and I'm studying medicine. And so if anyone has any questions related to the content which we're going to be covering today, or anything to do with subjects or even university, just feel free to ask any of those questions. So just a bit of an overview of what we're going to cover today. So we're going to start off with covering some topics mainly to do with Unit 4. So we'll start off with just a general introduction to the Unit 4 content and organic chemistry. Then we'll go on to focusing more on hydrocarbon skeletons and functional groups, then looking at the physical properties of these particular organic compounds and how physical properties of organic compounds are affected by the structure of what the particular organic compound is and its functional groups, so then relating that back to the first point. Then we're also going to be looking at some isomers, so having two different types of isomers and how this is going to affect their physical properties and their chemical properties. And then we'll finish up with looking at the important need to know organic reactions, which are obviously relate back to physical properties, isomers, and functional groups, and so the reactions which will occur will depend on all of those. There'll also be plenty of time for the Q&A about the content of the lecture, and then also just any general advice. So if you have any questions, just feel free to ask. So we'll start off with a bit of an overview of what organic chemistry is. So according to American Chemical Society, organic chemistry is basically just a study of the structure of properties, properties, composition, reactions, and preparation of compounds which contain carbon, so that including not only hydrocarbons but also compounds with any number of other elements, so that could be hydrogen, nitrogen, oxygen, halogens, phosphorus, silicon, and sulfur. So basically it's these compounds which have a carbon backbone, and based off this carbon backbone they then have functional groups which affect the physical and chemical properties and affect what reactions this particular compound can participate in. So we'll look at some general C to H skeletons, so our general basic hydrocarbon chains. And so our general hydrocarbon chains are known as alkanes. And so an alkane means a chain which just has a single bond between any carbon molecules. And so when we look at the naming properties for these, we can see that they have the same general suffix on the end, so that being ane, A-N-E, and then they've just changed the prefix for each of these depending on the number of carbons in the backbone of the molecule. So for example, if there is 1 carbon in the molecule, it will be methane. If there is 2 carbons in the molecule, it then becomes ethane. 3 becomes propane. 4 becomes butane. 5 becomes pentane. 6 becomes hexane. 7 heptane. 8 is octane. 9 is nonane. And 10 is decane. And so what you'll notice about these is that as you delve further into organic chemistry, these prefixes don't just apply to our general basic alkane molecules, but also apply to other molecules such as our alkynes, our alkenes, our alcohols. Just like any organic compound, they'll follow the general same prefix structure depending on the number of carbons in the backbone of the molecule. We can also see, looking back at this, in the far right column, we've got condensed structural formula. And so we can not only draw these as shown in the middle box with the extended structural formula, where it's very spaced out and shows how the molecules are arranged in space. So for example, methane being a singular carbon molecule with 4 hydrogens bonded around it. We can instead show a condensed structural formula where we can write CH4, or like going on to ethane, CH3, CH3. So not entirely condensing it down to its molecular formula, in which ethane would be C2H6, but instead a condensed structural formula where it's showing still the general structure of the molecule in a condensed version, so being CH3, suggesting that there is a carbon molecule with 3 hydrogens bonded to it, connected again to another carbon molecule with 3 hydrogens bonded to it. Next, we can look at some functional groups, which we have, and we will delve further into what these are. But just to start off with, we'll just go through a general overview of what these functional groups are and what sort of features make them what they are. So the first one we can see is we've already looked at alkanes, so now we can look at alkenes. So alkenes, very similar to alkanes, except their functional group is a carbon-to-carbon double bond. So this basically means that somewhere along the carbon backbone, there is a double bond between 2 of the carbon atoms anywhere along that carbon molecule. And so an example of this could be ethene, which would be a CH2CH2, and so that would be having 2 carbon molecules with a double bond between them, and then due to the molecule wanting, each atom wanting to have a stable octet, there would then be 2 hydrogens bonded to each of the carbon molecules in order for the carbon molecules and the hydrogen molecules to attain stable octet. The next one we can look at is alkynes. And so alkynes, also very similar to the alkanes and alkenes, except they have a triple bond between at least one of the carbons in the carbon backbone. So an example we could have is but2-ine, so that being CH3, CH3. So what this is suggesting is that we have a carbon molecule which is then bonded to 3 hydrogens and another carbon molecule. And then the second carbon molecule along has a triple bond between the second carbon molecule and the third carbon molecule. So if there is a second carbon molecule and a third carbon molecule with a triple bond between them, we would name it as a and then the last one having another carbon on the end with 3 hydrogens bonded to it, we'd name it as but2-ine as opposed to but3-ine, because we want to name the location of this triple bond, so whether the triple bond is located between the first carbon and the second carbon, or the second carbon and the third carbon. If it was between the third carbon and the fourth carbon, we'd just name it as if it was between the first carbon and the second carbon. But we will talk about this a bit more further in depth a bit later. But basically, if it's between the first one and the second one, you'll name it as it being the first one. If it's between the second one and the third one, you'll name it as it being on the second one. And so it's always just about favouring the lowest number for the naming of any organic compound. The next one we can look at is alcohols. So alcohols have what's known as a hydroxyl group. And so a hydroxyl group is composed of an oxygen bonded to a hydrogen. And so this oxygen can be located anywhere along an alkane, alkene, or alkyne chain. And so it will just be this this single bonded oxygen and hydrogen attached anywhere along the carbon chain. And so an example which we could look at could be ethanol. So this being a basic ethane molecule, so 2 carbons. And so normally an ethane molecule would be C2H6, so having 2 carbons and 6 hydrogens. However, one of the hydrogen molecules gets replaced with a hydroxyl group, resulting in ethanol as opposed to ethane. The next one we can look at is aldehydes. So aldehydes have what's known as a carbonyl group. And so a carbonyl group is a double bonded oxygen group. And so in an aldehyde, this is an end chain carbonyl group. And so what this means is the carbonyl group is located on the final carbon of the chain of the molecule. So whether that be an alkane, alkene, or alkyne, the double bonded oxygen or carbonyl group will be located on the last or first carbon of that chain. And so an example of this could be ethanal, so that being an ethane molecule, so a CH3CH3 molecule, except it would then become CH3COH. And this is because we would have the first carbon in the molecule just being this carbon with the 3 hydrogens bonded to it, but then the next carbon along would obviously have a bond to the other carbon, then it would have a double bond to the oxygen, and then to complete its stable octet, it would then need to have a hydrogen bonded. And so because the carbonyl group is located on an end of a chain, so in ethanal, obviously you could only have an aldehyde, it couldn't be located in the middle of the chain. In ethanal, it would be on the end of the chain, and so hence it would be ethanal with the carbonyl group being on the end of the chain. And so we can contrast this with the next one, which is known as ketones. And so ketones are much like aldehydes in that they have the carbonyl group, but the carbonyl group is not an end chain carbonyl group. In this case, it must be a mid-chain carbonyl group. So this means it can be located in any carbon along the carbon chain, except for the first one or the last one. So an example we can look at with these is propone. And so propone being a propane molecule with 3 carbons along the carbon chain. The first one and the last one are just a carbon with 3 hydrogens bonded to it, but the middle one obviously is bonded to the 2 carbons on either side of it, but then it's also got the double bonded oxygen attached to it. And so because that carbonyl group is in the middle of the chain, it's known as a ketone, and because it's 3 carbons long, it's propone. And so it wouldn't be an aldehyde because the carbonyl group is in the middle of the chain as opposed to being on the end of the chain. The next one we can see is carboxylic acids. So carboxylic acids have what's known as a carboxyl group. And so what you'll notice about the name of carboxyl is that it sounds a bit like carbonyl, and hydroxyl combined. And so that's basically exactly what this is. And so in a carboxylic acid, on the end of a chain, and it will always be on the end of a chain of a molecule, you'll have the end carbon of the carbon backbone double bonded to an oxygen and single bonded to a hydroxyl group. And so this is what's then known as a carboxyl group. So carboxyl group being the carbon double bonded to an oxygen and single bonded to a hydroxyl group. And so these are called carboxylic acids. And so an example of these which we can have is ethanoic acid. So ethanoic acid would be CH3COOH. And so the way this would be set up would be you'd have a carbon with 3 hydrogens bonded to it and then bonded to another carbon which would have a double bonded oxygen and a single bonded hydroxyl group. So because it's a general ethane molecule, all single bonds with 2 carbons in it, it's ethane, but then the end of the chain is changed to have a carboxyl group, which makes it an ethanoic acid as opposed to being an ethane molecule. The next one we can look at is halogens, halogen groups, which can be put onto an alkane chain to make what's known as a haloalkane. And so a haloalkane is quite a simple molecule. It's just the exact same as your general alkane molecule, except one of the hydrogens from the alkane chain has been replaced by a halogen. So any of the halogens from the periodic table, so common ones are generally chlorine and bromine. So an example which we've got here is chloroethane. So in chloroethane, we've taken a basic ethane molecule and we've swapped one of those hydrogens to a chlorine, and so instead of it being CH3CH3, we get ClCH2CH3. And so this could be written a number of ways. It could also be CH2ClCH3. Basically, whichever way it can be written, it's still representing chloroethane because it's suggesting that one of those carbons only has 2 hydrogens and has a chlorine instead. And so with these, if it was longer than 2 carbons long, if it was going into then 3 carbons long, you would need to name the location of the halogen molecule, so of the halogen atom, in order to correctly name the molecule. So for example, if it was a propane molecule and one of the hydrogens on the first carbon or the last carbon was substituted with chlorine, you'd get 1 chloropropane. If it was on the second carbon atom along, then you'd get 2 chloropropane. The next one we can look at is esters. And so what esters are is that they are basically like a combination between a carboxylic acid and another added on alkane chain. So what happens with these is they have part of an alkane chain followed by part of a carboxyl group, so that being a carbon with a double bonded oxygen and then a single bonded oxygen. But then from that single bonded oxygen onwards, they then continue with another carbon chain, being another alkane chain. And so this is what's formed, what's known as an ester. They can also be called alkanoates, and so that's just based off their naming structure. And so, for example, we can look at methyl ethanoate, and so with methyl ethanoate, we'd have CH3COOCH3, and so that's saying that the methyl group is this first part of the molecule, which is the part of the molecule which is attached after the C double bonded O single bonded O. So it's like the leftover part of the molecule, and then the ethanoate part is sort of what we call like the main chain of the molecule. So this part at the front here, the part which is connected to the carbon with the double bonded oxygen. So, for example, if we're looking at methyl ethanoate, methyls being this part on the end here. So if we're looking at this, it would be one carbon over here. And ethanoate is the start of the molecule where we'd have a carbon here and a carbon here. So ethanoate being 2 carbons long. And so that would be with that double bonded oxygen. And so methyl ethanoate would have 2 carbons at the start. The first carbon would have 3 hydrogens bonded to it. The next carbon would have the double bonded oxygen to it, and then a single bonded oxygen in the middle of the chain. And so that forms the ethanoate part. Then from that single bonded oxygen in the middle of the chain, you'd bond a carbon to it, and then bond 3 hydrogens to that carbon to form the methyl part of the molecule. The next one we can look at is nitriles. So nitriles have what's known as either a cyano group or a nitrile group, can be called either. And so nitriles are basically just your simple alkane, alkene, alkyne molecules, but instead they've got a triple bonded nitrogen atom on the end of the chain. And so when we look at this, we'd have the chain down one end, and then we just have a triple bonded nitrogen on the end. And so an example of this could be something like ethane nitrile. So we just name it as the ethane molecule because it's got 2 carbons in the chain. And so the first one would be a carbon with 3 hydrogens bonded to it, then bonded to the next carbon, which would have a triple bonded nitrogen to it. And so we can notice with this one, the last carbon on the chain, the one with the triple bonded nitrogen, does not have any hydrogens bonded to it because it's attained its stable octet. It's got 1 bond from the other carbon and 3 bonds from the nitrogen. And so because it needs 4 bonds to achieve its stable octet, that is enough bonds. It's got 1 from the carbon and 3 from the nitrogen. The next one we can see is amines. And so amines have what's known as an amine group. And so this is based off ammonia. And so what happens with these is we can either have 1 R group, 2 R group, or 3 R groups. And so R groups being carbon chains branching off the nitrogen molecule. And so basically what happens with an amine is that you start with the original NH3 molecule, so the ammonia molecule, and each of those hydrogens from the original NH3 molecule can be replaced with carbon chains. So, for example, if we're looking at something like ethylamine, we've only had 1 of the hydrogens from the NH3 molecule replaced by a carbon chain. So we've got a CH3, then CH2, so a 2 carbons long, basically along this section here, and then bonded to a nitrogen, and then there'd be a hydrogen bonded here and a hydrogen bonded here. We could also have other options where we can have a carbon chain bonded here, a carbon chain bonded here, and then a hydrogen bonded here. Or we could have a carbon chain here, a carbon chain here, and a carbon chain here. So it can be 1, 2, or all of the hydrogens from the original ammonia molecule, which can be replaced with carbon chains, or it can be 2, or it can be only 1. Then building off this, we can go and look at amides. So amides are like a bit of a combination between having a carbonyl group, but also having an amine group. And so this is where we can have the carbon, which is bonded closest to the nitrogen, having a double bonded carbonyl group. So we're still basing this off the original ammonia molecule, so an NH3 molecule, and we are successively replacing the hydrogen molecules with carbon chains. However, we can have 1, 2, or 3 of these hydrogens replaced, same with an amine, but one of these chains will have closest to the nitrogen molecule a double bonded oxygen group, so a carbonyl group. And so an example of that which we can look at is ethanamide, so that being having 2 carbons, and then the carbon closest, so if we had a carbon here, and then nitrogen here, the carbon closest to the nitrogen would have a double bonded oxygen, and then we'd have a hydrogen bonded of each of these potential locations for R groups. And then same with amines, we could also have a carbon group based off either of where the other hydrogen groups were located in the original ammonia molecule. So that summarizes all of our functional groups and just gives you a brief overview of what's coming up. So now we'll look at these in a bit more depth and our proper naming conventions for these as well. But to start off with, before we do that, we need to look into what we know as the IUPAC rules. And so these are the rules for naming organic compounds and basically just for understanding the structure and how that affects the name of any organic compound. So these are our main 4 rules which we have, and then we also have some supplementary rules to assist in making the naming of these a bit more coherent. So our first step in naming any organic compound is that we need to identify what the parent chain is. And so the parent chain is going to be whatever the longest carbon chain is that's present in the molecule. So whether that be 5 carbons long, making it a pent molecule, or 10 carbons long, making it a dec molecule, or 2 carbons long, making it an F molecule. So that's just looking back at our original naming of the alkanes, so the methane, ethane, propane, butane, pentane, continuing on. And so that will determine generally what the prefix is going to be for the molecule. The second step is that you need to recognize and correctly prioritize what the functional groups are that are present. So we'll look more into the prioritizing a bit later, but recognizing what the functional groups are that are present is very important. So that's looking along the molecule and identifying, do we have a hydroxyl group, or do we have a carboxyl group, or a carbonyl group, or is there nitrogen in this molecule also coupled with a carbonyl group, which may make it an amide as opposed to an amine. And so it's really just identifying what functional groups are present and so what class of molecule you believe this may fit into. And then prioritizing them would be determining, well, if they also have say for example, if they were to have an halogen group and then they were to also have an amide group, which one's most important in giving the suffix for the name, and so which one's most important in our naming conventions, and would that make us consider this an amide or a haloalkane molecule in preference. And so in that case, obviously an amide is a lot more substantial, has a lot more impact than a halogen in a molecule, so obviously the amide would take priority over the halogen in that particular circumstance. The next thing we want to look at is the number of carbons on the chain. And so this is something that's done directionally. So the lowest number is going to be given to the carbon with the highest priority functional group. So this is saying that when we count along the chain, we're going to want to count from the end with the highest priority functional group. So if our highest priority functional group is on the right-hand side, we count the right-hand side as being 1, 2, 3, 4, etc., etc. We'd have to count from right to left. If our highest priority functional group was on the left-hand side, we'd have to count from left to right because we want to number our functional group so that it's at the lowest possible number. But if we have functional groups on the opposite ends of the molecules, we need to determine which one's the highest priority. And so hence the one with the highest priority will be the one which will be named with the lowest number. The final step is adjusting the name based on branches or functional groups that are present, and this is done by listing their prefixes in alphabetical order with numbers. So we list the functional groups out the front that may be prefixes, and those prefixes will always need to be put in alphabetical order with numbering at the beginning. So if it's on the first carbon, for example, if we have a methyl group on the first carbon, we would have to name it, on the second carbon, we'd have to name it 2-methyl and then the rest of the chain. If we had a methyl group and an ethyl group, as we're naming them in alphabetical order, we have to put the ethyl group before the methyl group, as they would be named in alphabetical order. Something also important to note with these is that if we were to have 2 ethyl groups, hence if it was to be diethyl, that would still put ethyl, or dimethyl, that would still put methyl ahead of ethyl. So if we had dimethyl, that would still put ethyl ahead of methyl, because if we were to have an ethyl group and 2 methyl groups, it would still go ethyl dimethyl, even though the dimethyl is making the alphabetical order switch the other way around, because we're just looking at the actual part of the prefix, not the multiplier of the prefix. So now we can look at some of our supplementary IUPAC rules. And so this is talking about extra rules which help in making the naming a bit more clear. So if we have more than one side chain or functional group, we need to add a prefix which relates to the number of them. So as I was previously talking about before, we can use, if there's 2 of a particular functional group, we have to use di, 3, tri, tetra, 4, etc. And just depending on how many there are of that particular functional group, and then list all the numbers of where they are located. So if you were to have a methyl group on the second carbon and a methyl group on the third carbon, you'd have to say that it's a 2,3 dimethyl at the beginning. And so you don't count the prefixes when figuring out the alphabetical order. So as I said before, if you had an ethyl group but then a dimethyl group, you'd still put ethyl before dimethyl, even though alphabetically that wouldn't seem right, because ethyl comes before methyl in the alphabet. The next thing we need to note is that you use commas between numbers. So for example, if we're saying that we've got a methyl group on the second carbon and a methyl group on the third carbon, you'd have to say 2, 3 hyphen dimethyl. So that also leads to the next point, which is using a hyphen between letters and numbers. So anywhere where you separate the numbers from the letters, you're going to have to put a hyphen. So if you're saying that there is a chlorine group on the second carbon, you'd have to call it 2 hyphen chloro, whatever the rest of the chain is. It's also important not to put spaces between prefixes. So if you have a prefix ahead of a particular molecule, so for example, you had a methyl pentane molecule and it was on the second carbon, it would be 2 hyphen methyl pentane. Methyl pentane would not have a space in between it, it would just be methyl pentane being one word. Then when we're looking at double and triple bonds, that being alkenes and alkynes, the number which has to be used to name where the double or triple bond is located is going to be the lower number out of the 2 carbons that the bond is between. So for example, if the double bond is between the first and second carbon, you would name it as it being between the first carbon. If it was between the 4th and the 5th carbon, you'd say it's at the 4th carbon. If it was between the 2nd and the 3rd, you'd say that's at the 2nd carbon. So it's always going to be the lowest number between the 2 carbons. The next important thing to note is that if the functional group could not be on any other possible carbon, don't write the number. So for example, if we're talking about an ethane molecule and we're saying that there's a double bond between, and we're changing that into an ethene molecule, so we're putting a double bond between the 2 carbons, which there are. Obviously the double bond, if there's only 2 carbons, the double bond can only be between those 2 carbons, so hence we would just call it an ethene molecule. We wouldn't have to call it one ethene. And finally, the branch is going to be the same way, it's going to be named the same way that a separate molecule with that structure would be named, but with the suffix "il" instead of "ane." So for example, if you have a branch which has 3 carbons, so a 3-carbon branch coming off a normal carbon molecule, it would be a propyl group because it's like propane, but it's a branch coming off another chain, so it would be named as a propyl group. So if you had a carbon molecule which is 10 carbons long, but on the the 5th carbon in, you've got a branch with 3 carbons on it, you call it 5-propyl decane to show that it's got 10 carbons along the main backbone, but on the 5th carbon in, there is a branch which is 3 carbons long. So now we'll just look at a bit of a summary of the functional groups and particular prefixes and suffixes which can be used for these. So when we look at our functional groups, when we look at the first one, we can see we've got a carboxyl group. And so generally with carboxyl groups, we'll be using the suffix of oic acid. However, in this case, in some cases, we will be using the prefix of carboxy, and so that really just depends on the prioritization of a particular functional group. So whether that is a low priority functional group, and hence we might have to use the prefix, but generally we'd be using the suffix of oic acid. With amides, generally the suffix will be amide. However, sometimes the prefix of carbamoyl or amido is used, and so that's just obviously the prefix will be used typically if it is a lower priority functional group. Same with nitriles, we're typically using the suffix of nitrile. However, sometimes the prefix of cyano is used for when it's a lower priority functional group. Aldehydes, we're typically using the suffix of al, but sometimes we may use the prefix of oxo, and same with ketones, they may also sometimes get the prefix of oxo, but typically they'll be using the suffix of -one, which is generally a lot more reliable to use the suffix of -one because it really denotes between aldehydes and ketones, because the suffix shows that they're a different class of organic compound, whereas the prefix doesn't show that very explicitly. For the hydroxyl functional groups, so for alcohol molecules, we're typically using the suffix of -ol. However, there's lots of complex alcohol molecules, and so the prefix of hydroxy is actually used quite commonly when alcohols and the hydroxyl group is a lower priority functional group, and that's just because there's lots of very, very complex molecules that have alcohol groups or hydroxyl groups in them, and so hence the hydroxy prefix gets used quite frequently, but typically you would want to preference using the suffix of -ol just because that's your normal naming convention for an alcohol. So unless there's a higher priority functional group, you wouldn't want to use the prefix of hydroxy. The next one is amines, and so typically they'll just have their suffix of amine. However, these ones also do have this thing similar with alcohols where they are involved in very complex molecules sometimes, and so the prefix of amino is also quite common as well. That's one which is used sometimes, but generally in this syllabus in particular you'll be focusing on using the suffix of amine. Next we've got alkenes. So alkenes typically will have the suffix of -ene. However, sometimes you'll have those prefixes of alkenyl. So that being typically if there's a branch coming off the molecule, they'll have the alkenyl prefix. Same with alkynes, they normally have their suffix of -ine, but typically if there's a branch, they'll use the prefix of alkenyl. So first of all, we're going to start off by looking at some examples of our functional groups to look at how these work in basically some examples of what molecules are and how you would actually go about drawing these and their different structural types. So we've got 2 main structure types which you'll be required to be able to recognize and one which you'll be required to be able to actually draw yourself. So we've got on the left, we've got the structural formula, and then we've got the skeletal formula. So the structural formula is showing each individual atom and how it is bonded to every other atom, whereas the skeletal formula shows this but without any letters to specifically denote what these are. And so with the skeletal structure, we're saying that we're assuming that any hydrogens are just there, they're not explicitly ever shown in this, and then we're assuming that the carbons is the end of any of the molecule, so the two ends of these for ethane being the two carbons, and then the hydrogen just being assumed to be there. With longer molecules, they'll be forming a zigzag shape, and so any ends of the molecule and any points of the molecule will be assumed to be carbons. And so with these, you only need to know how to draw the structural formula, but you also need to be able to recognize the structural formula and draw the structural formula. With the skeletal formula, you only need to be able to recognize that one. You don't need to be able to draw it. Our next example which we can look at is 2-methylbutane. So 2-methylbutane is a molecule which we've got here, where we've got 4 carbons along the carbon backbone, and then along on the second carbon in, we've got what's known as a methyl group, so that being a group of methane basically, but it's a separate branch off the original molecule. And so we can see this structure on the left here. The way this has been laid out is a little bit different from the one which we saw with ethane, where we've specifically got these sticks and letters to specifically show the exact layout of the molecule. With this one here, we've got a slightly condensed structural formula, so you will commonly see these ones as well. And so basically what these are is we've got a carbon, and we're just saying that these 3 hydrogens are bonded off this carbon here. So not necessarily that it's anything different from the other one too much, it's just condense it down so that you can draw them in a smaller space. And so for example, the next carbon along, it's saying that it has been bonded to one other hydrogen, and so that hydrogen would be drawn in the other formula as being sticking out the bottom here. And same with this carbon here, this is methyl group here is drawn as coming off of this second carbon, and these hydrogens would be surrounding this particular carbon molecule, but it just hasn't been drawn like that, just so it can be condensed down. Then on the right, we've got the skeletal formula. So the skeletal formula of this, showing that we've got one carbon here, the next carbon here, another carbon here, and another carbon here, so that being 1, 2, 3, 4 carbons. Then we can see we've got this chain sticking off, so that end of that line being another carbon there, so that being this particular methyl group here. And so what we can notice about the difference between this and this is that this is actually just a flip of the other molecule. So instead of counting 1, 2, 3 and saying that it's a 3-methylbutane molecule, 3-methylbutane doesn't exist because we always want to preference the lowest number on the methyl chain. So we'd actually be naming it from right to left instead, and we want to preference the lowest number for the methyl group, so we'd name it as 1, 2, and so that methyl group's on the second carbon, it will be a 2-methylbutane molecule. So the next one we're going to look at looks very, very complex when you first look at it, but when you break down the naming of this one, it's actually a lot simpler than it first appears to be. And so what we can see here is that we've got a molecule which is named as 7-ethyl 2,2-dimethyl 4-propylnonane. And so when you're faced with a long and big molecule name like this, or a big molecule, or if you were shown just this structure here and it's a big molecule like this, the first thing you always want to look at is what is at the end of the molecule. What is the suffix for this particular molecule name? And so we can see that the suffix is nonane, so that being a 9-chain long alkane molecule. And so we can see if we count along this chain down the bottom here, we want to find the longest possible continuous chain. So we can count 1, 2, 3, 4, 5, 6, 7, 8, 9. And so that's 9 carbons long along the longest possible chain. We could also count it 1, 2, 3, 4, 5, 6, 7, 8, 9, or 1, 2, 3, 4, 5, 6, 7, 8, 9. Or if we counted from here, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's plenty of ways, but the longest possible chain which can be formed is 9 carbons long, so we're going to be saying it's a nonane molecule. Next, we can look at what all these different functional groups are, which we have. So it's saying on 7, we have an ethyl group. So on the 7th carbon along the molecule, we have an ethyl group. So we can count along and we can go 1, 2, 3, 4, 5, 6, 7. We can see on the 7th carbon along, we've got 2 carbons branching off of that. And so those 2 carbons branching off are what we know as an ethyl group, because it's like an ethane branch. But when it's a branch, we change it to ethyl. And so that's the 7-ethyl. Next, we can see we've got a 2,2 dimethyl group. So it's saying that on the 2nd carbon, we've got 2 methyl groups. So 1, 2, we've got a methyl group on this side and a methyl group on this side. And so it's important to note that this is not considered an ethyl group, because although they're on the same carbon, they're on opposite sides. So one carbon, one of these methyl groups is on this side, one of these methyl groups was on this side. If they were both on the same side, so if we went carbon and then bonded another carbon here, that would not be known as a methyl group. That would then be known as an ethyl group, and so instead it would just be a 2-ethyl. But because they're on opposite sides, they're 2 separate groups. That's a methyl group there, and that's a methyl group there, and so hence it's 2,2-dimethyl. The next one is saying 4-propyl. So it's saying we've got a 3-carbon chain long branch on the 4th carbon along the chain. So we can go 1, 2, 3, 4. And we can see we've got 1, 2, 3 carbons branching off the 4th carbon along the main chain. And so this here would be our propyl group, because it's like a propane chain, being 3 carbons long, except it's a chain, so and it's branching off, so it's a propyl group. So hence we end up with 7-ethyl, 2,2-dimethyl, and 4-propyl, and then nonane being the entire length of the main chain. So it's really important when you're faced with these complex ones like this that you focus on breaking down the naming, because they do appear very complex at the beginning, but once you break down the naming system and into its constituent parts, it makes a lot more sense and it makes it a lot easier to figure out what it is. The final one we're going to look at is 3-ethyl 2-methylheptane. So we'll do the same thing to break this one down. So we'll look at what the end of the molecule says. So we've got heptane. So that meaning that the longest possible chain along the backbone of this molecule is going to be 7 carbons long. So we can count 1, 2, 3, 4, 5, 6, 7. So that's 7 carbons long at the longest point along the chain. We could also double check here, 1, 2, 3, 4, 5, 6, 7. That part there could also be the longest part of the chain. We could count 1, 2, 3, 4, 5, 6, 7. That there could be our longest chain. Either way, our longest possible chain is always going to be 7 carbons long. So hence it's going to be heptane at the end of the molecule. The next thing we want to look at is what our functional groups are. So we've got an ethyl group and a methyl group. So when we look for our ethyl group, we can see that's on the 3rd carbon along. So we want to count 1, 2, 3. We can see that's the 3rd carbon along. We've got 2 carbons bonded off this, a 2-carbon chain. And so on the 3rd, 1, 2, 3 carbon along of the chain, we've got an ethyl group. And so that creates this 3-ethyl at the start. Then going along, we've got a 2-methyl group. So we've got a methyl group, a single carbon branch on the second carbon along the chain. So we can go 1, 2, and this here we can see we've got a methyl group located here as we've got 1 carbon branching off the main chain. And so that's what our extended structural formula would look like for this particular molecule. The next thing we want to look at is what would our skeletal formula look like for this particular molecule. So we can see this one here is actually a flip of this molecule here, much like the other time. So we can be counting from left to right, from right to left as opposed to left to right, because if we look for the ethyl group, we can see the carbons being on the points and on the ends of the molecule. So we'd have 1 carbon, 2 carbons, 3 carbons, and we can see we've got a branch located here. So 1 carbon, 2 carbons. So that 2 carbon long branch there would be our ethyl group. So 1, 2, 3, our ethyl group's on the 3rd carbon along the chain. And then our methyl group is going to be on the 2nd carbon along the chain. So going 1, 2, we've got 2 methyl there. And so that methyl group being the end of that stick there. So that just shows how we can name these molecules based on their skeletal formula or their structural formula, and how they can be shown to be counted from left to right or right to left, depending on whichever way they've been drawn. They're the exact same molecule, just drawn in different ways. Next, we want to look at alkenes versus alkynes. So alkenes being our double bonded between the carbons, so at least 1 double bond, and alkynes being at least 1 triple bond between a carbon. So for example, we can contrast ethene and ethine. So ethene being a double bond between the 2 carbons of the molecule, and ethine being a triple bond between the 2 carbons of the molecule. And so what's important to note with these here is that ethene is going to be C2H4, whereas ethene is going to be C2H2. And so this is because we want to attain that stable octet with the carbon molecules and the hydrogen molecules. So obviously each hydrogen molecule shares an electron, a valence electron with the carbon, but the carbon, each of these carbon molecules already gets 2 shared electrons from the other carbon molecule due to the double bond, so it only needs 2 other electrons to be shared with hydrogens in order to attain its stable octet, so that's why it's C2H4. With ethine, there's only 1 more electron which needs to be shared in order to attain the stable octet, because the carbon molecules already get 3 shared electrons from each other due to the triple bond, and so that's why ethine is going to be C2H2. So next we can look at alcohols. So alcohols have what's known as the hydroxyl group, and so the naming convention for this is putting the suffix of -ol. So for example, ethanol being a molecule which has got 2 carbons, it's just a general ethane molecule, except one of the hydrogens has been replaced by the hydroxyl group. And so the general structure is an R group, so an R group being any alkane, alkene, alkyne chain, with then a hydroxyl group attached to it. And so we've got 3 different classes of alcohols, or types of alcohols, and so these are known as primary, secondary, and tertiary. So primary alcohols are going to be alcohols in which the carbon atom, which is bonded to the hydroxyl group, is only bonded to 1 other carbon atom. So for example, or no other carbon atoms. So for example, with our primary alcohol here, we've got methanol, and so methanol, the carbon atom which the hydroxyl group is bonded to, is not bonded to any other carbon atoms. So methanol being the one and only exception. Ethanol would also be a primary alcohol, as we can see that the carbon atom which is bonded to the hydroxyl group is only bonded to one other carbon atom. Next, we can look at the secondary alcohols, where the carbon atom bonded to the hydroxyl group is bonded to two other carbon atoms. So an example of this would be something like this one here, which would be 2-propanol, and so that's saying that we have a 3-carbon chain long molecule, and on the second carbon along there is a hydroxyl group, making it a 2-propanol molecule, which is a secondary alcohol. And this is because the carbon which the hydroxyl group is bonded to two other carbon atoms. And so if this hydroxyl group was to be bonded on the first or last carbon atom, and hence making it 1-propanol, it would then become a primary alcohol, because if it was bonded to the first or the last carbon, the carbon which the hydroxyl group was bonded to would only be bonded to one other carbon. Then finally, we've got tertiary alcohols. So tertiary alcohols have a carbon atom which is bonded to the hydroxyl group being bonded to 3 other carbon atoms. And so typically this will only occur if you have a some kind of branch, like a methyl group or an ethyl group, on the same carbon that the hydroxyl group is bonded to. So for example, this molecule here being methyl propan-2-ol, so saying that we've got a methyl group on a propanol molecule and a hydroxyl group on the second carbon into the propanol molecule. And so that's because this carbon here is bonded to the hydroxyl group, and it's also bonded to 1, 2, 3 other carbon atoms, hence making it a tertiary alcohol, because the carbon with the hydroxyl group bonded to it has the carbon bonded to 3 other carbons. So some examples which we have of alcohols is propan-2-ol or 2-propanol. So these are 2 different ways which you could name this particular molecule. I would say the best way is the first name, so the propan-2-ol, just because that makes it very clear and very explicit that you are naming the alcohol as being on the second carbon along the chain, whereas with more complex molecules, when they become very complex and you put the 2 out the front and make it 2-propanol, that makes it very difficult to follow what the numbers are actually naming. So I would preference calling it propan-2-ol as opposed to 2-propanol. But they are both correct ways which you can name this molecule. And so when we look at this molecule, we can see that the reason that it's called propan-2-ol is because we've got a propane chain, so 3 carbons along the carbon backbone. And then we can see that on the second carbon along, we've got a hydroxyl group as opposed to a hydrogen. And so this is what makes this propan-2-ol. So the 2 denoting that it's on the second carbon, and the ol suggesting that it's a hydroxyl group. The next one we can look at is ethane 1,2-diol or 1,2-ethane-diol. And so this one's employing our supplementary IUPAC rules. And so it's saying that we've got 2 hydroxyl groups in this ethane molecule. So I would say name it with the first name which I've got here, which is ethane 1,2-diol, because this specifically shows that the 1,2 is specific to the alcohol groups, whereas if this was a more complex molecule, it could easily get muddled up with putting the numbers out the front. So we can see that on the first carbon, we've got a hydroxyl group, and on the second carbon, we've also got a hydroxyl group, hence making this ethane 1,2-diol, the di meaning that there is 2 hydroxyl groups in this particular molecule, and the 1,2 suggesting that it's on the first carbon and on the second carbon. The next class of molecules we can look at is aldehydes. So aldehydes have what we know as the end chain carbonyl group, so that being a double bonded oxygen. And so our example which we have for these is ethanal. So ethanal being this molecule here down the bottom, where we can see we've got 2 carbons making that the ethane part of the name. And then we can see instead of having 3 carbons on the second carbon in the chain, we've got 1 carbon and a double bonded oxygen instead. And so that end-chain carbonyl group meaning the double bonded oxygen group. And so the general structure of an aldehyde is that they will have an R chain, so any alkene, alkane, alkyne type chain, followed by the final carbon on the chain having a double bonded oxygen and a single bonded hydrogen. So some examples which we have of these is butanal. So butanal being this molecule here where we can see we've got 1, 2, 3, 4 carbons along the main chain, that being the butane part of the name, and then we've got the double bonded oxygen and single bonded hydrogen on the end of this molecule, making this known as an aldehyde molecule because the carbonyl group is on the end of the molecule. So that is butanal. The next one we're looking at is propanal. So similar concept, except we've got a propane chain as our main chain. So 3 carbons along the main carbon backbone. And then completed with an oxygen group, a double bonded oxygen group on the end of the molecule. So that being our carbonyl group there, making it a propanal molecule as opposed to our normal propane molecule. The next one we want to look at is the similar molecule, which is ketones. So similar to aldehydes, it's got a carbonyl group. However, ketones have a mid-chain carbonyl group as opposed to an end-chain carbonyl group. So for example, naming, we use the suffix of -one. So for example, butanone being this molecule down here, we've got 4 carbons along the main chain. So the butane part being the 4 carbons along the main chain, and then butanone saying that we've got a double bonded oxygen on one of the middle carbons along the chain. So the middle carbon along the chain being one of these two, we don't need to name with a number of which carbon this is located on because it will either be on the second one or the third one, and so the third one would be named as the second one because if we count from this direction we'd go 1, 2. If we count from this direction, we'd get 1, 2. We can't count from this direction because we get 1, 2, 3, and we always want to preference naming with the lowest number. So this molecule would be butan-2-one, but we just name it as butanone because it's always going to be butan-2-one. And so the general structure of these is that we have an R group, so that being our carbon chain, followed by our carbon in the middle of that chain with the double bonded oxygen, so the carbonyl group, and then followed by the rest of the R chain, so that being our R prime group. So some examples which we have of these is like what we looked at before. So we've got butanone, so butanone being our 4 carbons along the main chain, so the butane molecule, with the double bonded oxygen on one of those middle chains. The next one we can look at is being propanone. So propanone being our general propane chain, 3 carbons along the main chain making the propane part of the molecule, and then the ketone part being the double bonded oxygen, the carbonyl group, on the middle of the chain of the molecule, which changes this from being a regular propane molecule to being a propanone molecule. Our next functional group we can look at is the carboxylic acids, and so they have a functional group which is called an end chain carboxyl group. And so that is the end carbon of the chain has a double bonded oxygen, so a carbonyl group, and a single bonded oxygen and hydrogen, so a hydroxyl group. And so as we briefly said before, the carboxyl group is the name carboxyl comes from it being a carbonyl group and a hydroxyl group, so combined to get carboxyl. And so the naming for these is we have the suffix of oic acid. So for example, ethanoic acid, this molecule shown here. So we can see the ethane part comes from the 2 carbons along the main chain. Instead, now we've substituted the end of the molecule to have an N-chain carboxyl group, which has changed this from an ethane molecule to an ethanoic acid molecule. And so the general structure for these is that we have an R group, and so the R group is just the general chain of any alkane sort of group, followed by the carbon with the double bonded oxygen carbonyl group, and then the single bonded hydroxyl group, so oxygen and hydrogen, making that N-chain carboxyl group. And so hence that would form the carboxylic acid. So some examples which we have of these is butanoic acid. So that being this one here, where we can see we've got 1, 2, 3, 4 carbons along the main chain, and then on the end of the molecule we can see we've got a double bonded oxygen and a single bonded hydroxyl group, making it a carboxylic acid. So hence the butane part comes from the 4 carbons along the main chain, and then the oic acid part comes from the carboxylic acid group, the carboxyl group at the end of the molecule. The next one we can look at is propanoic acid. So propanoic acid being this molecule here with 3 carbons along the main chain, so that being the propane part of the molecule. And then we can see we've got the carboxyl group on the end of the molecule with our carbonyl group here, our double bonded oxygen, and our hydroxyl group, our single bonded oxygen to hydrogen, making this a propanoic acid molecule from the original propane molecule. The next one we want to look at is esters. So esters are what we know as alkyl alkanoates based on their naming conventions. And so their functional group is going to be quite complex. It's a carbonyl group, which is attached to a single bonded oxygen on a mid-chain carbon. So the way which these are named is we have an -yle plus an anoate section. So that's where the alkyl alkanoate part comes in. So for example, methyl ethanoate. So if we look at what methyl ethanoate is here at this diagram at the bottom, we can see the methyl part is this additional section here, whereas the ethanoate part is the section which has the carbonyl group attached to it. So we can see we've got 1 carbon here, 1 carbon here, so 1, 2 carbons, that being an ethane chain, but then this one's got a double bonded oxygen and then the single bonded oxygen in the middle of the chain. So this part is the end of the name, the ethanoate part, and then this part over here, which doesn't have the carbonyl group, is just connected to by the single bonded oxygen to the rest of the chain, is what is the methyl part of that group. So that's why it's named methyl ethanoate. And that's because the highest priority functional group part of the chain is always named with the suffix, so that being the ethanoate part, this has got the carbonyl group and is also attached to the other mid-chain oxygen, and so that's what makes this part the ethanoate part and this part only the methyl part. And so our general structure of these is we'll have an R group, and then with our carbonyl group and the mid-chain oxygen, single bonded oxygen, and then we'll have an R prime group following on from that. So the R group in methyl ethanoate being the ethanoate part, and then the R prime section being the methyl group. So some examples which we've got here is butyl propanoate. So butyl propanoate being the butyl part being this additional chain over here, which doesn't have the carbonyl group, so 1, 2, 3, 4, and then the propanoate part being the suffix, the most important part of the molecule, 1, 2, 3, that's our propane chain, and it's got the carbonyl group bonded here and the mid-chain single bonded oxygen here, which is what makes this part the propanoate part, because it's got the propane chain with the carbonyl group and the mid-chain oxygen, whereas the butyl group only has the butane chain and then is connected by this single bonded mid-chain oxygen. The next one we can look at is ethyl propanoate. So ethyl propanoate being this molecule here, where we can see if we look for the ethyl section, that's going to be the section which doesn't have the double bonded oxygen, it doesn't have the carbonyl group. So that's this section over here, where we can see 2 carbons long. It's an ethane chain, but it's the ethyl group because it's a branch. And then the propanoate part is going to be the propane chain with the carbonyl section and the mid-chain oxygen. So 1, 2, 3 carbons long, that's the propane, and then the propanoate is due to this carbonyl group and the single bonded mid-chain oxygen. The next one we want to look at is nitriles. So nitriles have the functional group of a triple bonded nitrile, so just a nitrile group. And so these ones are named pretty easily. It's just the name of the chain with nitrile at the end. So for example, propane nitrile, which we've got shown here, is just going to be a propane molecule, so 3 carbons along the main chain with a triple bonded nitrogen on the end of the molecule. So the nitriles will always be an end chain nitrile group. The triple bonded nitrogen will always be the last thing on the end of the chain, and that's just because of the way which the stable octet works. Nitrogen only needs 3 bonds in order to attain its stable octet. Carbon only needs 4 bonds to attain its stable octet. So if you were to put the nitrile in the middle of the chain, the carbon would just end up with too many bonds because you can't triple bond to a carbon which already has 2 other bonds from the carbons if it was in the middle of the chain. So that's why the nitrogen has to be bonded on the end of the molecule. So an example which we can look at of these here is, for example, heptane nitrile. So heptane being that it's a 7 carbon long chain, so 1, 2, 3, 4, 5, 6, 7. So we've got 7 carbons along that chain. And then the nitrile meaning that we've got this nitrogen bonded onto the end of this molecule. And so as we can see, this is a condensed structural formula. It's showing that we've got CH3, so this carbon is bonded to 3 hydrogens. Then the next one being CH2, 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 and then the final carbon having no hydrogens bonded to it because it's got the triple bond to the nitrogen, and it's already got a single bond to the previous carbon, so hence it's got its stable octet of 4 shared electrons along with its already 4 valence electrons. The next one we can look at is ethane nitrile. So ethane nitrile obviously is just a general ethane chain, so 2 carbons long, and then we can see that the final carbon on the molecule, which could be either of these carbons, because it's ethane, it's going to always be an end chain functional group, no matter which carbon it's bonded to, is going to be on this carbon here, and we can see it's triple bonded, so it's attained the stable octet for all of those particular atoms, and so that's what makes that ethane nitrile. The next one we want to look at is amines. So amines being having the functional group called an amino group, which is based on NH3, but with 1 or more hydrogen being replaced by alkyl groups. So the naming for these is alkyl amine, so the alkyl group with amine on the end. So for example, ethylamine being this molecule down here, where we can see we've got 2 hydrogens along here, so an ethane chain, then with the amine group at the end of the molecule. So that nitrogen has that ammonia molecule has 1 of the hydrogens replaced with this ethyl chain, and it's still got its 2 existing hydrogens. So there's particular steps that need to be followed in order to name these, because they can go many different ways depending on how many groups are, how many of the hydrogens are replaced with R groups. So the first thing we need to do is name each alkyl group. So for example, in ethylamine, we've only got one alkyl group, so we just name it as ethyl. Then you need to place each alkyl group in alphabetical order and use multipliers when they're required. So for example, if you've got an ethyl group here, and then if you were to have a methyl group here, you would need to say ethyl methylamine, putting them in alphabetical order. If you had an ethyl group here, a methyl group here, and a methyl group here, you'd have to call it ethyl dimethylamine. So to say that you've got one ethyl group and then two methyl groups, and obviously putting that in alphabetical order, not based on the multipliers, based on the original stem name of the alkyl group. Then the final thing you have to do is just add the suffix of amine to the end of the name. And so we can see this here is just our general structure. So we've got an R group, and it's based off an ammonia molecule. We've got an R group, and then we've got these two hydrogen groups remaining here, but either of these can also be replaced with R groups. So whether that's an R group there, an R prime group there and a hydrogen, or an R group here, an R prime group here, and an R double prime group here, just depending on how many of the hydrogens are replaced with the alkyl groups. So with amines, we've got primary amines, secondary amines, and tertiary amines. So similar with our concept of primary, secondary, and tertiary with alcohols, amines have a similar kind of concept. So a primary amine is going to mean that the nitrogen atom is bonded to one carbon atom. So it's saying that the nitrogen from the original ammonia molecule, only one of the hydrogens from NH3 has been replaced by an alkyl group. So the nitrogen is only bonded to one other carbon atom. In secondary amines, the nitrogen atom is bonded to two carbon atoms. And so what this means is that two of the original hydrogen molecules from the original ammonia molecule have been replaced by alkyl groups. So instead of it being the original NH3 molecule, it's only got one of those existing hydrogens left from the NH3, because two of those have been replaced by alkyl chains, or by like an alkane-based chain. Then a tertiary amine is going to mean that the nitrogen atom is bonded to three carbon atoms. And so this means that from the original ammonia molecule, there is no existing hydrogen atoms left over. So from the NH3, all of those three hydrogens have been replaced by alkyl groups. So each of these, it's nitrogen with an R group, an R prime group, and an R double prime group. So making it a tertiary amine because the nitrogen is bonded to three carbon atoms from three separate bonds. So some examples which we can look at here is we'll start off with a basic one. So this being methylamine. So this basically means with methylamine, we've got the original nitrogen molecule from the ammonia, and we can see that we've got two hydrogens left over, and one of the hydrogens from the original ammonia molecule has been replaced with what we can see is a methyl group. So a methane chain branch, so one carbon long. The next one we can see is ethyl methylamine. So with this one, it's named in alphabetical order, ethyl methylamine. So we know ethyl means that it is a 2 carbon long branch, and methyl means that it's a 1 carbon long branch. And so because we've got two branches, we can identify that this means that there must have been two hydrogens from the original ammonia molecule replaced with alkyl groups. So we can see from this diagram here, from the structure, we've got one original remaining hydrogen on the ammonia molecule, but then we can see we've got one replaced with a methyl group here. So we've got a singular carbon branched off from over here. And from this one here, we can see we've got two carbons branched off from this section here. So that being our ethane chain, our ethyl section, and that being our methyl chain there, the methyl section of the name. So hence this is ethyl methylamine. And so what we can notice about these is that methylamine, the nitrogen is bonded to only one other carbon atom, hence making this a primary amine. With ethylmethylamine, the nitrogen is bonded to two other carbon atoms, hence making this a secondary amine. Our next functional group we're going to look at is amides. So amides have a carbonyl group attached to an amine molecule. And so the way which these are named is we have the name of the alkane plus amide. So for example, and that makes it an alkanamide. So for example, ethanamide. So ethanamide being this molecule down the bottom here, which we can see we've got an ethane chain being 2 carbons long, and then it's connected to the amine part of the molecule, where there's only been one of the hydrogens from the original ammonia molecule replaced with this ethane chain. But then we can also notice that the closest carbon to the original ammonia molecule and to the nitrogen atom has a carbonyl group, this double bonded oxygen on it, hence making this an amide as opposed to an amine. So with these ones here, we also need to have a naming process because they are quite complex to name due to all of the substituted groups which can go in the location of where the hydrogens were in the original ammonia molecule. So it's very similar to naming amines, where first of all we must identify the main chain. So that's the main chain is the one which contains the carbon with the double bonded oxygen, so the carbonyl group. And so that's obviously in ethanamide, that's this chain here where we can see we've got 2 carbons, the one closest to the nitrogen having the double bonded oxygen carbonyl group. We then need to number the carbonyl chain as carbon number 1. So this here being carbon number 1, that being carbon number 2, etc., etc. And that's just our prioritization of functional groups because we want to show that the amide section of this chain is the priority. The next thing we need to do is add the suffix amide to the main chain. So this is saying that we're putting amide on the end. For example, in ethanamide, we've got to say we've got amide on the end of the name to say it's based off the ammonia molecule. So for example, in ethanamide, we've got the ethane chain, and then we add amide to the end to say we've got this double bonded oxygen and this based off ammonia group. Finally, this is the one step which is quite different from the amines, but we have to use N to represent alkyl groups bonded to the nitrogen atom. And so that's in our more complex amines. So for example, this is going to be our main chain here because it's got the carbonyl group, but we can also have alkyl groups bonded off here, which won't have the double bonded oxygen in them. So they will just be a general alkyl group. So for example, we could have 1 carbon bonded off here, and so that would be an N-methyl group. So the N representing that the methyl group is coming off the nitrogen atom. And so the general structure of these can be shown in this small diagram over here, where we've got an R group, which has the carbon with the double bonded oxygen, so the carbonyl group. And so that's our main chain, it's bonded to the nitrogen. And then we can see here we've got R prime and R double prime. So the R prime and R double prime could either be hydrogen atoms to make that more close to the original ammonia molecule, or they could be alkyl groups, so being methyl groups, ethyl groups, propyl groups, etc. And it could be one or both of those that's replaced from the original ammonia molecule. So some examples we can look at with these, we'll start off with a simple one, that being methanamide. So what we can see with methanamide is we've got 1 carbon branched off the nitrogen molecule. And so this nitrogen molecule still has 2 original hydrogens from the original ammonia molecule. So it doesn't have any alkyl groups, it's just got the main chain. And so we can see the carbonyl group is there as well, making this an amide as opposed to an amine. and so this one here being methanamide because it's only got one carbon in its main chain. This one here, the next one, N-methylpropionamide, is a bit more complex in that it is got an N-methyl group. And so that's saying that we've got a methyl group branched off the nitrogen, so we've only got one original existing hydrogen from the original ammonia molecule. So when we look at the end, the suffix of the molecule, which is what we always do first, we've got propionamide. And so that's suggesting that our main chain, the chain with the carbonyl group, the double bonded oxygen, is going to be a propane chain. So it's going to be 3 carbons long. So that's 1, 2, 3, and then on the third one, we've got the carbonyl group, the double bonded oxygen, and then that is closest to the nitrogen, so we can see that's bonded to the nitrogen there. And instead of having a hydrogen here and a hydrogen here, we've replaced one of these hydrogens from the original ammonia molecule with a methyl group, so with 1 carbon, making that an N-methyl group because we name this as being N-methyl. It's a methyl group coming off the nitrogen atom. So that covers all of our functional groups. So now we're going to go into the physical properties of molecules. So these physical properties are going to depend on their functional groups which the molecule has, and this is due to intermolecular forces. So intermolecular forces are going to include dipole-dipole interactions, hydrogen bonding, and London dispersion forces, which are otherwise known as either just dispersion forces or van der Waals forces. And so stronger intermolecular forces in a molecule are going to result in decreased solubility in organic solvents, increased melting and boiling points, and increased solubility in water. So we'll look at these in more depth. So we can look at our dispersion forces first. And so this is a bit of a recap from grade 11, so from unit 1 and 2. But basically, just to recap on what you've learnt and as a bit of a reminder, because these are very important, when we discuss dispersion forces, we're talking about the force which exists between all types of molecules. So it's a force which occurs when there's intramolecular non-polar covalent bonding in molecules. And so basically, it's just this weak attraction between every single molecule which holds things together. And so the more electrons which a molecule has, the stronger its dispersion forces are going to be. However, dispersion forces are the weakest of all of the intermolecular forces. So if a molecule only has dispersion forces, it's not going to have very strong intermolecular forces compared with some other molecules which have a lot stronger intermolecular forces. The next one we can look at is dipole-dipole interactions. And so these occur when there's a partial positive and a partial negative dipole which occurs in a molecule, such as HCl, which is shown here. So because of an electronegativity difference between hydrogen and chlorine, there is an attraction of electrons to the chlorine part of the molecule because the chlorine part of the molecule draws the electrons towards it. This leaves the protons towards the hydrogen part of the hydrochloric acid molecule, making this have like what's known as a temporary dipole, where one side of the molecule is temporarily negative and the other side is temporarily positive. And so this means that the hydrogens from the hydrochloric acid molecule are attracted to the chlorines of neighboring hydrochloric acid molecules, forming the dipole-dipole interaction force. And so this is the middle strength of intermolecular forces. It's not the weakest, but it's not the strongest. And obviously this strength does increase with more electrons and greater electronegativity. Now, our strongest of the dipole-dipole interactions is what we know as hydrogen bonding. And so hydrogen bonding is a special type of dipole-dipole interactions, which occurs with molecules which contain a hydrogen bound to either an oxygen, nitrogen, or fluorine atom. And so we commonly see this in water molecules because there's intramolecular polar covalent bonding. And this occurs because there is such great electronegativity difference between hydrogen and oxygen that the oxygen or nitrogen or fluorine, depending on what the atom is, draws electrons towards itself so strongly, creating this very strong temporary positive and temporary negative in the molecules. And so this means that the either oxygen, nitrogen, or fluorine from one atom can be very strongly attracted to the hydrogens from other atoms, forming these strong, what's known as hydrogen bonds between the molecules. And so these are what we know in this syllabus as our strongest intermolecular force. And so when we compare our relative strengths and what they occur between, we can see we've got hydrogen bonding, dipole-dipole interactions, and London dispersion forces. So hydrogen bonding is going to occur between hydrogen atoms and oxygen, fluorine, or nitrogen atoms, and it's going to be the strongest of the dipole-dipole interactions. Then we've got our dipole-dipole interactions, which are just our standard dipole-dipole interactions, and they occur between partially oppositely charged ions, so meaning that ions with a substantial electronegativity difference, and so their strength of intermolecular force is going to be reasonably strong, but not as strong as the hydrogen bonding. And then our final one is the dispersion forces, and they occur when there's a temporary or induced dipole, and they have a fairly weak strength. Their strength does increase with larger molecules due to there being more electrons, but they will always be the weakest intermolecular force. And so we can look at the physical properties of organic compounds depending on what their intermolecular forces are. So we've got ionic compounds, and they've got ion-to-ion attraction between the ions, and they've also got London dispersion forces. So we don't really look at ionic compounds in too much depth, but they do have stronger than hydrogen bonds, and so they will have the highest melting and boiling points because they have an ion-to-ion attraction between those particular ions. But we don't really look at those too much, we just need to know that they exist and that the ion-to-ion attraction is stronger than hydrogen bonds. The next one we've got is covalent compounds, which contain hydrogen bonds, so that being an oxygen, nitrogen, or fluorine bonded to a hydrogen in a particular covalent compound. And so this will mean that there will be hydrogen bonds present and London dispersion forces present. There may also just be general dipole-dipole interactions present as well, depending on the particular molecule. And so they will have the second highest melting and boiling point. If we're just considering hydrogen bonds, dipole-dipole interactions, and London dispersion forces, then we would say that they have the highest melting and boiling point. The next one we can look at is the polar covalent compounds. So polar covalent compounds are going to have a dipole-dipole interaction between the dipoles which are created by partially charged ions. So this will be a slight difference in electronegativity, resulting in partial positivity and partial negativity in the molecule. They'll also have London dispersion forces like any other molecule, and so hence they are the next in the rank of height of melting and boiling points. Then finally we've got our non-polar covalent compounds, and so these don't have any other intermolecular forces other than the London dispersion forces, and so because the dispersion forces are quite weak, they are going to provide these compounds with the lowest melting and boiling points. Next up, we're going to look at isomers. So isomers are molecules which we consider to be basically the same. So basically the same meaning that they have the exact same molecular formula, but the arrangement of atoms is different. And so there's two different types. We've got our structural isomers, so they've got the same molecular formula, but a different structural formula. So we've got the same atoms, the exact same number of them, but just different bond arrangement between them. Then our next one is the stereoisomers. So they've got the exact same molecular formula, but just a different spatial arrangement of atoms. And so when we look at stereoisomers, we're going to specifically be looking at the geometric isomers for this particular syllabus. So when we look at structural isomers, we can consider something like C4H10. And so we can see with C4H10, we've got 4 carbons in this molecule, 10 hydrogens in this molecule. And so we can easily say, well, that would describe a butane molecule because it's got 4 carbons. But what we haven't considered is how branching can affect what the molecular formula is going to be. So it could also describe methyl propane. And so that's because with our butane molecule, we could either have a straight chain where we've got 4 carbons along a straight chain backbone, and then the 10 hydrogens bonded along there, or we can have 3 carbons along the main backbone, and then a methyl group attached to the middle of the propane chain, making this a methyl propane molecule instead. And obviously, as we have the same number of carbons and they're all single bonds in both molecules, we're going to have the same number of hydrogens as well. And so C4H10, without saying that it's specifically butane or methyl propane, we're unable to know what the particular molecule would actually look like with its arrangement of atoms due to bonding. So C4H10 could either be butane or methyl propane. Our next one which we want to look at for isomers is our geometric isomers, so our subtype of stereoisomers. And so with geometric isomers, we've got either the cis or the trans isomers. And so what we can notice is with these 2 molecules here, they've both got 4 carbon atoms, and they've each got 8 hydrogen atoms. And so they're both C4H8. They both are butene molecules, so they've both got a double bond between, and they're both 2 butene molecules, so they both got a double bond between the second and the third carbon. However, the one thing which we can notice is different between these 2 different isomers is that the cis-2-butene has the carbons on both sides, so when the arrangement from the double bond occurs, we've got these carbons on the same side, and then we've got the hydrogens on the same side. However, when we've got trans-2-butene, we can see that we've got 1 hydrogen on this side, and 1 hydrogen on this side, and then 1 carbon on this side, and 1 carbon on this side. So the cis isomers are going to have the carbon methyl, or like the carbon groups on the same side and the hydrogen groups on the same side, whereas the trans isomers are going to have the carbon groups on opposite sides and the hydrogen groups on opposite sides. And so these types of geometric isomers will only occur when there has been a double bond within a molecule. So the final thing that we need to look at today is organic reactions. And so this is because understanding organic reactions and reaction pathways is not only going to enable us to understand what's happening in certain reactions and what sort of organic reactions are shaping the world around us, but also allows us to narrow down what organic molecules are through a series of different tests. So for example, carboxylic acids, they're obviously an acid, they're going to have a pH above 7. So if we tested the pH of an unknown solution and the value was above 7, we know a carboxylic acid is going to have a pH below 7 because it's acidic. So if we test the pH and the pH is above 7, we know that's basic, it's not going to be a carboxylic acid. So before we look at the organic reactions though, we need to have an understanding of saturated and unsaturated compounds. So saturated compounds are going to be compounds that contain only single bonds. So this basically means that all carbons have 4 single bonds. The maximum number of hydrogens possible for the molecule are possible due to there being only single bonds. So the molecule is entirely saturated with hydrogens. Whereas unsaturated compounds will contain at least 1 double or 1 triple bond. And so they're not fully saturated with hydrogens, they can be either monounsaturated compounds, so meaning they have one double bond, or polyunsaturated compounds, which means they've either got multiple double bonds or triple bonds. And so by definition, an alkane is going to be saturated because it's got all single bonds along the backbone of the carbon molecule, and alkenes and alkynes are always going to be unsaturated molecules because they've got at least one double bond or one triple bond along the main carbon chain. We also need to look at primary, secondary, and tertiary carbons. And so when we look at these, we're always using the convention of 1 degree, 2 degree, and 3 degree to mean primary, secondary, and tertiary. So those are just like our shortened names for representing what primary, secondary, and tertiary are. And so a primary carbon atom is going to be the carbon atom which is connected to one other carbon atom. Or for example, in methane, no other carbon atoms. A secondary carbon atom is going to be connected to 2 other carbon atoms. And then a tertiary carbon atom is going to be connected to 3 carbon atoms. And so these are used to describe the location of functional groups. So as we've spoken about before, with our alcohols we have primary, secondary, tertiary, and with our amines we've got primary, secondary, tertiary. We can also do this with haloalkanes as well to describe the location of the halogen groups. So this concept of primary, secondary, and tertiary is very useful in describing our functional group locations. So now going on to our organic reactions which we need to know. So the first one which we're going to look at is a substitution reaction, and so it's a substitution of alkanes in order to make haloalkanes. So what alkanes are is they are a very unreactive molecule, and so this is because they have high stability in their hydrogen to carbon bonds, so in their hydrocarbon chain. And so we've seen that before in that an alkane is fully single bonded. And so this means that they're very unreactive. They're not going to react very easily, so hence they need what's known as a catalyst. And so their catalyst is going to be UV light. So this reaction will only occur in the presence of UV light, whether that being sunlight or specifically artificially created UV light. And when they are in the presence of UV light, they can react with halogen gases to form what's known as our haloalkanes. So, for example, if we started off with an ethane molecule and we were to put it in the presence of UV light and chlorine gas, so Cl2, we could form a chloroethane molecule. And so when we form the chloroethane molecule, we're switching out one of the hydrogens for a chlorine atom. And so when we switch out one of the hydrogens for a chlorine atom, we then are left over with one of the chlorine atoms from the Cl2 and the hydrogen atom which has been taken out of ethane, leaving us with chloroethane and HCl. So our main product which we would produce would be chloroethane, and then our byproduct which we would produce would be HCl, or hydrochloric acid. The next one we can look at is the substitution of haloalkanes to make alcohols. So there's 3 types of these ones which we can look at, and in each case the halogen on the haloalkane is replaced by another atom or a group of atoms. So we've got the substitution of haloalkanes with hydroxide, and in this case a primary haloalkane will form a primary alcohol, a secondary haloalkane will form a secondary alcohol, and a tertiary haloalkane will form a tertiary alcohol. We also have a substitution of haloalkanes with ammonia in order to make amines. So for example, if we take something like chloroethane and we combine this with ammonia, so NH3, we can replace the chloro group with the amine group, so with the NH2 from the NH3, leaving us with ethylamine, and then we'd have a leftover hydrogen from the NH3 because we've only put in NH2 into the molecule, and we'd have the leftover chlorine from the original chloroethane molecule. So our main product would be ethylamine, and then we'd have a byproduct of HCl, being the leftover hydrogen from the NH3 and the chlorine from the chloroethane. The next one we want to look at is the substitution of haloalkanes to make nitriles. And so this is done by substituting haloalkanes with cyanide. So for example, again, starting off with chloroethane, if we are to use KCN, which is potassium cyanide, in ethanol, so the potassium cyanide must be in ethanol in order for this reaction to occur. We can then combine that with the chloroethane, and this will produce ethane nitrile. So what happens here is that the chlorine group is lost along with these two hydrogens here, and it's replaced with this triple bonded nitrogen group here, and then we end up with a KCl, potassium chloride, as a byproduct to this reaction. So our main product would be the ethane nitrile, and then our byproduct would be the leftover halogen from here, or whichever group this was from here, the potassium, our halogen from here, the chlorine, along with our potassium, which is left over from here. So the KCl being potassium chloride being our byproduct to the reaction. The next one we can look at is addition reactions. And so addition reactions of alkenes to make haloalkanes. And so this is done by producing haloalkanes by combining alkenes with halogens. So for example, if we start off with a molecule like ethene, we can do a dihalogenation, and so, or just known as a halogenation. And so this is where we take our ethene molecule, for example, so it's got a double bond in the middle, and what we do is we break this double bond, and then in order to ensure that the stable octet is attained, we can substitute in these bromine groups to then make this a dibromoethane. So this is incorrectly labeled here where it says bromoethane. That should say dibromoethane to specifically show that we have two halogen groups here, two of these bromine molecules. Our next one down is where we're adding HBr. So instead of adding Br2, we're adding HBr. And so HBr is going to mean that we're doing a hydrohalogenation. So it's hydrogen and a halogen being substituted into the ethene molecule. And so what's happening here is we break the double bond. And so once we break the double bond, we need to complete the stable octet. And so we do this by adding in the hydrogen and the bromine, causing this to form bromoethane. And so when we look at these addition reactions, we need to consider something called Markovnikov's rule. And so what Markovnikov's rule says is that the hydrogen atom is going to be more likely to bind to the carbon which has more hydrogens bound to it already, and the halogen is going to be more likely to bind to the carbon which has fewer hydrogens already bound to it. So for example, when we look at something like this molecule here where we've got a propene molecule, if we add HCl to a propene molecule, we can form both 1 chloropropane and 2 chloropropane. And so both of these will be formed. However, we'll have a main product, so our major product, and we'll have a minor product. So there'll be substantially more of one of these possibilities produced than the other. And so there'll be substantially more 2 chloropropane produced as opposed to 1 chloropropane. And so this is because 2 chloropropane, on the second carbon along on the molecule, there's only one hydrogen bonded to it, whereas on the third carbon along, or the first carbon along on the molecule, there's two hydrogens bonded to the carbon. And so Markovnikov's rule is saying that hydrogen is going to bond to the carbon which already has more hydrogens bound to it, so it's going to bond to the CH2 part of the molecule as opposed to the CH part of the molecule, resulting in 2 chloropropane as opposed to 1 chloropropane. So we'll end up in this reaction with producing mostly 2 chloropropane. However, there will be a very small amount of 1 chloropropane produced. The next one we can look at is another addition reaction, where we've got addition of alkenes to make alcohols. And so in this particular addition reaction, we add water to alkenes in order to produce alcohols. But what we can notice with this here is that we can't just add water as it is, because if we're adding ethene to a water molecule, ethene is fairly unreactive with water as well, because water is fairly unreactive. So we need an acid catalyst. So we're using H3PO4 just because this is a fairly unreactive acid, but it can be used as a catalyst. And so when we add ethene to H2O under an acid catalyst, we can produce ethanol. And so as we can see here, we don't need to apply Markovnikov's rule to this particular circumstance, being ethene, because each carbon atom has the same number of hydrogens bonded to it. However, if we had a larger molecule, we would need to apply Markovnikov's rule to this particular circumstance to show which particular one would be the major product. So whether the hydrogen would be bonding to which particular carbon and which one the hydroxyl group would be bonding to. And so what we've done in this particular reaction is, like the halogenation ones, we've broken this double bond, and then we've formed a single bond here, and then added the hydrogen and the oxygen and the hydrogen from the water in order to make this ethanol molecule. The next one we can look at is an addition reaction of alkenes to form polyalkenes. And so this is known as a polymerization reaction. We're producing polymers. And so this is talked about a lot further into Unit 4, so I won't delve into this too much, but I will just briefly give an overview of what this is. So basically, if you combine alkenes with a catalyst such as TiCl3, you can form what's known as a polyalkene. So for example, here we're looking at a propene molecule. If we combine multiple propene molecules under this catalyst, we can form a long chain of alkene molecules in which they have these methyl groups placed incrementally along a very long chain. And so these are used in very many industrial applications to create plastics, fabrics, all those types of things, because they can create very long continuous molecules. The next addition reaction we want to look at is an addition reaction of alkenes to make alkanes. So this is adding H2 under a platinum catalyst or a nickel catalyst, just any inert metal, in order to create an alkane. So we've got ethene, and because ethene would be unreactive, we've obviously got that catalyst, and when we add H2, we're breaking this double bond and adding these two hydrogens in order to make this into an ethane molecule as opposed to an ethene molecule, and to reattain that stable octet. The next reaction we can look at is an esterification reaction. So an esterification reaction is a reaction in which we can make esters through a reaction between alcohols and carboxylic acids. So the general rule for this is that we combine an alcohol plus a carboxylic acid, and so the alcohol part will form the alkyl group of the name, and the carboxylic acid will form the alkanoate part of the name. So for example, if we were to combine ethanol and methanoic acid, we would need to use a concentrated H2SO4 catalyst, so a concentrated acid catalyst, in order for this reaction to occur, and this would then produce an ester, being ethyl methanoate. So the ethanol part becoming the ethanol part becoming the alkyl group, the branched off chain, and then the methyl part becoming the methanoate group on the end. And then this reaction, obviously we'd be breaking the bond here and breaking a bond here, so we'd also produce water in this particular reaction as a byproduct. And so this reaction can be reversed to go back the other way, and so we can add water and an ester to make a carboxylic acid and an alcohol. So this is a reversible reaction. Our next reaction we want to look at is making amides. So in order to make amides, we can combine carboxylic acids and either an amine or ammonia under high heat as a catalyst in order to make an amide. So for example, when we combine the carboxylic acid and either the amine or the ammonia, we're breaking the bond where the OH, the hydroxyl section is on the carboxylic acid, and we're removing that, and then we're joining that to where the hydrogen was on on either the amine or the ammonia. And so this performs the amide, with the part with the double bonded oxygen being the carboxylic acid section, and the part with the ammonia and the nitrogen being either the original amine molecule or the ammonia section. And as we can see, we've removed a hydrogen from the amine or the ammonia molecule, and we've removed the hydroxyl group from the carboxylic acid molecule. And so that leaves us with a byproduct of water in this reaction. And so this reaction is also reversible in the forward direction. It's a condensation reaction. We can reverse the reaction back again as a hydrolysis reaction, so we can add water and an amide in order to form either ammonia or an amine and a carboxylic acid. We've also got a reduction reaction to make amines, so we can combine a nitrile with hydrogen gas under either a platinum or a nickel catalyst, so any inert metal catalyst, in order to create an amine. And so this would just be simply removing the nitrogen group from the end of the, removing a part of the nitrogen group, so some of the bonds from the nitrogen group, and adding in the hydrogen atoms to make it into the amine molecule. We can also do a reduction of alkenes, so this being very similar to our substitution reaction before, where we add hydrogen gas under a platinum or nickel catalyst in order to form an alkane. So that being, for example, forming ethane from ethene. We can also undergo an elimination reaction to form alkenes. So this is like reversing our addition reaction. So we can start off with a haloalkane, and we can use potassium hydroxide in alcohol. And so by adding the haloalkanes such as bromoethane to potassium hydroxide in alcohol, we can form ethene by removing the halogen group from there and breaking the single bond, forming a double bond instead. And so that forms our byproducts of KBr, so potassium bromide, and some hydrogen atoms. The next one we can look at is an oxidation of primary alcohols to make aldehydes or carboxylic acids. So this is a two-step oxidation reaction, and this one occurs only with primary alcohols. So there is a separate reaction with secondary alcohols. So for example, if we take a primary alcohol such as ethanol, we can oxidize it using acidified potassium dichromate or dichromate ions, and this results in the formation of an aldehyde. So in this case, ethanal. And so we can either take the ethanal, or whatever aldehyde it is, out of the reaction at this specific point in time, or we can continue to oxidize it under the same conditions but at higher concentrations of dichromate ions in order to form ethanoic acid or whatever carboxylic acid it has formed. And so in that case, you can then either form an aldehyde or a carboxylic acid. Our next one is the oxidation of secondary alcohols to make ketones. So if we look at this one here, we've got propan-2-ol, and so this is a secondary alcohol. And so secondary alcohols can only undergo a one-step oxidation process. So we have the exact same reaction conditions, so dichromate ions acidified. However, this will form a ketone, so being propanone in this case. So in the acidification, in the acidified potassium dichromate oxidation process, this is only a one-step process for a secondary alcohol, resulting in the production of a ketone. And so we don't have one for the tertiary alcohols because they can't be oxidized. Now finally, we want to look at the complete combustion of alkenes, alcohols, and alkanes. So basically this is just a recap on basically grade 9, grade 10, grade 11 content, but it's always important to just have a recap of this. So we can take a hydrocarbon and we can combine it with oxygen. And so when you see a reaction where the only products are carbon dioxide and water, and one of the reactants is oxygen, you always know that it's going to be a combustion reaction. And so these are pretty common with any molecules which just are made up of carbon and hydrogen, so any hydrocarbon molecules. And so that's why these are related to our organic reactions. So this is taken directly from the syllabus, and this is basically a summary of all of the organic reactions. I would recommend drawing this out, making your own version of this in order to show a summary of how you of all these different reactions, and in order to help you memorize these, because you won't have a copy of this for the exam. So another thing we can do is we can use these organic reactions to help identify solutions. So in order to identify the difference between an alkane or an alkene, we can use bromine water. And so this is because we know that the reaction of an alkane with bromine gas requires UV light, whilst the reaction of an alkene with bromine gas does not require any catalysts. And so we can put the samples of bromine water with our two samples of either the alkane or alkene, so our unknown solutions, in a dark place. And so if the color changes, we'll know that there is, whether it's an alkane or an alkene, and then we can put it into sunlight, and if the color is lost, that can also show whether the reaction required UV light or whether the reaction did not require UV light. The next thing we can also do is we can use our primary, secondary, and tertiary alcohol oxidation to determine which type of alcohol we have. So if we have 3 unknown alcohols, we can use potassium dichromate or potassium manganate. And so they each have different colors when they change oxidation states. So you can put the unknown solution into a tube with the alcohol and with the potassium dichromate, and if there's no color change, we'll know it's a tertiary alcohol because tertiary alcohols can't oxidize. If it changes color twice, we'll know it's a primary alcohol because primary alcohols oxidize twice. And if it can only be oxidized once, we'll know that it's a secondary alcohol because secondary alcohols can only be oxidized once. So this is just a summary of what we've done today. So we've looked at the hydrocarbon skeletons and functional groups. We've looked at physical properties, specifically intermolecular forces. We've looked at isomers, our structural and geometric isomers. And then we've looked at the important organic reactions being oxidation, reduction, addition, condensation, elimination, and substitution reactions. And so some important things to take away from this lecture today is that it would be a good idea to memorize the IUPAC naming rules and practice using these rules in order to name organic compounds. And it would also be a good idea to memorize and practice organic reaction pathways. I would recommend doing this by making your own summary diagram like shown in the previous slides from before. So thank you for watching everyone, and good luck.